Section 7.8 Tetrahedral complexes. When all four ligands are different in a tetrahedral complex, there can be two enantiomers. Over here, this transmetal center is bonded to four different ligands, A, B, C, and D. And then this is the mirror image of the structure on the left. These two cannot be superimposed on each other. Therefore, we have a chiral center here, and we say these two are enantiomers to each other. When two chelating ligands are present, there can also be enantiomers. So over here, this may be a little confusing. This ligand and this ligand are exactly the same. Both are bidentate ligands. So we have A and B linked to each other. And then over here, you have A and B linked to each other. So again, this is a bidentate ligand with 2 points of attachment to this transition metal. So in this case, it's also a chiral molecule. And this transition metal is the chiral center. Why is that? Well, you can clearly see this is the mirror image of the structure. And there's no way to superimpose one on the other. So we say this is also a pair of enantiomers. They can both rotate polarized light. So how do we determine if a molecule is a chiral or achiral molecule? We just need to examine whether this molecular structure has any SN improper rotation symmetry element. So if it contains S1, S2, S3, or S4, S5, etc. improper rotation symmetry element, then this molecule is achiral. If a molecule does not have any improper rotation symmetry element, then this molecule is chiral. For example, hydrogen peroxide, H2O2, is actually chiral if its carbon-carbon single bond is frozen at a very low temperature. Well, but of course, at the room temperature, the carbon-carbon bond can rotate freely, so you will not be able to observe the chiral property of this H2O2. Now, just remind you, S1 is you do a C1 symmetry operation followed by a reflection with respect to a symmetry plane perpendicular to the C1 axis. So C1 actually is doing nothing. So basically this is just symmetry plane. Alright? So S1 is equivalent to a sigma symmetry plane. S2 is rotating the molecule 180 degrees first, followed by a reflection with respect to a symmetry plane perpendicular to the C2 axis. So S2 is equivalent to the center symmetry I. Why? Because when you do a C2 rotation about the z-axis, you actually change the xy coordinates to negative x and negative y. And then after you do a reflection with respect to the xy plane, you change the sign of z to negative z. So after a S2 operation, you go from xyz to negative x, negative y, negative z. So that's just the operation with respect to the center symmetry.